Welcome back. So last time we started, or we finished, interference in 2 and 3 dimensions, and we talked about it kind of qualitatively. I would like to do an example of interference in 2 dimensions here. So here's the setup. You have two speakers 2 meters apart and in phase with each other. So let's just draw something. So here's speaker 1, and here is speaker 2, and they are 2 meters away from each other, so that's 2 meters. Both emit 700 hertz of sound into a room where the speed of sound is 341 meters per second. Okay? A listener stands 5 meters in front of the speakers, so the listener would be 5 meters here, 5 meters away. Not only that, 5 meters in front of the speakers, 2 meters to one side of the center. So the speaker doesn't stand right in the middle, rather the speaker stands right here. Right here. 2 meters. So this is 2 meters. 2 meters. So sound waves will leave this speaker all the way to where the listener is. So they travel from here to here. This is R1. Let's call this one speaker 1. This one will be speaker 2 here. And so this thing here will be R2. R2. Let's calculate R1, R2, and then see what we get. All right, so here is R1. So this is 2 meters. The speakers are 2 meters apart. This is the middle, so this is 1 meter. So this has to be 1 meter here. This is 5 meters from here to here. So it's a simple Pythagorean theorem application. So you get 1 squared plus 5 squared square root. Let me get my calculator. We get 1 squared is 1 and 5 squared is 25. So 26 square root. That gives me 5.099. So 5.1. 5.1 meters. Let's see what this speaker, how far it travels, this R2. So this is 5 and this is what? You got 2 plus 1, so that's 3. So 5 squared, which is 25, plus 3 squared, which is 9. And you take the square root of that, and that gives me 5.83. So R2 will be 5.83. And remember, the displacement, or delta phi, the phase, delta phi was, if you remember, it was 2 pi divided by lambda times delta r plus delta phi 0. All right? So we have seen that. Delta phi 0 is the phase of the first minus the phase of the second, but if they are in phase, it means they don't differ here, so this is 0. So since they are in phase, then this part here, delta phi 0 will equal to 0. So we get delta phi will equal to 2 pi divided by lambda times delta r. Now, if this happens to be a multiple of 2 pi, then we will get constructive interference. Otherwise, it will be destructive interference if they differ by a pi. So, well, let's see what we get. First of all, I need lambda here. I know that the speed of sound is 341 and the frequency is 700 hertz. So let's calculate lambda. Lambda times f is v. So lambda will be v over f, and that's 341 divided by 700, and you get 341 over 700. That gives me 0.487 meters. That's the wavelength. And so let's plug it in. we get 2 pi divided by 0.487 times delta r. Delta r is the difference between the distances traveled. So 5.83 minus 5.1. So 5.83 minus 5.1. So get delta phi will equal to 2 pi times, let's see what this number is. So 5.83 minus 5.1 gives me 0.73. And then you divide that by 0.487. And I get about 1.5, right? 1.5, which is 3 pi. So is this constructive or destructive interference? The answer is it is destructive interference because it is it's not 2 pi, it's actually 3 pi, which will be destructive interference. They differ by half a wavelength. They differ by, one of them traveled more than the other, basically by a wavelength plus a half, which will be destructive interference. Okay. How do I know it's a wavelength and a half? Well, delta r divided by lambda is 1.5, so delta r is 1.5 times lambda. Now, if the speakers started out of phase to begin with, so two minuses will make it right, or 2 wrongs will make it right, if you like to say that. But they started out of phase, and then they are shifted by a pi. So to begin with, they're starting with, if they are out of phase, meaning delta phi there is a pi here, so you will be, instead of being 0, you will be adding a pi. This would make it 4 pi, and so it will be in phase. Okay? So that is that. So if they started out of phase to begin with, it will be constructive interference. However, now it is destructive interference. My last topic will be beats. So this is interference in space. You see, you have 2 sources here. If you stand here, it would be destructive interference. If you stand here, maybe something else. Here it's something else. Here it's something else. Maybe here it's something else. If you come here, it's something else. You're moving in space, and you find it's constructive or destructive interference. For beats, we will take, now the sources will not have the same frequency. They will differ a little bit. And you will, let's say the first source is here, the second source is here, and you're standing here, or maybe here, right? So there are waves coming towards you, and you're just standing here, you don't move. But suddenly you hear louder sound and a quieter sound, a louder sound and a quieter sound, just as time goes by. You don't have to change and move around in space. So the spatial part is not affecting the constructive or destructive interference pattern. Rather, it is the time factor. So it's like interference in time, which we call beats. So let me erase here. And I would like to just talk about some these beats here. So in general, you can have 2 waves. Wave 1, which has maybe some amplitude times the sine. Maybe it's a different wavelength, k1x minus omega 1 t plus some phase. Let's call it phi 10. And then the second wave will have similar thing, d, and then it's so this one is the first one, and this is the second one, and you have maybe k2 x minus omega 2t plus phi 20. Now the person will be standing somewhere, so we want to study the wave somewhere in space. So we will choose that point to be the origin. We're not going to change and move around, so we might as well just call that particular point to be the origin. And so we will just make the following assumptions to simplify. X is equal to 0. So this part here will go away. Number 2, omega 1 is close to omega 2, but not equal. it's close to omega 2, but omega 2, but not equal. The third assumption we're going to assume is that the phases here, the intrinsic phase phi 1 will equal to phi 2, and they would be equal to each other, and they're just equal to pi. You can choose it to be whatever you like. We chose pi for a reason that you will see in a moment. So let us write d1 with this simplification. So with this assumption, x is equal to 0, so this part goes away, so we just have a times the sine of negative omega 1 times t plus phi 1, 0, which is equal to pi. But here is the reason we chose pi, just to get rid of this negative sign, which is annoying. The sine of an angle plus pi will be the sine of the negative of that angle. So this will simply become a times the sine of omega 1 times t. And similarly for this one would be a times the sine of negative omega 2 times t plus pi, and that's equal to a times the sine of omega 2 times t. Omega 2 times t. And now I'm going to add them. I want to know, what do I get when I add the two waves? They interfere with each other. Interference, you just superimpose two waves, put two waves together, one on top of the other, add them, and see what you get. I need to refer to this identity again. The sine of alpha plus the sine of beta was equal to the cosine of, what was it? Alpha minus beta divided by 2, and then times the sine of alpha plus beta divided by 2. And let me make sure I have it correct. I have the identity correct. I sometimes forget it. And it looks good. It looks good. Oh, there is a 2 in front. There is a 2 here. I mean, you could verify these identities, these half angle and formulas and so on. You can easily verify them. Okay, so I'm going to use that. I'm going to add this and this. So I will have a and a in front, so that we'll have a 2a in front. So when we add them, we just have a 2a in front. And then the cosine of something. And then the sine of something. Okay. The cosine will be the cosine of alpha minus beta over 2. The over 2, I took care of it. And then alpha minus beta, so omega 1 minus omega 2, or omega 2 minus omega 1, it does not matter. Just put omega 2 minus omega 1. Cosine is an even function, so cosine of negative theta equals to the cosine of theta. The sine is just the sum of the two, so it's omega 1 plus omega 2, or omega 2 plus omega 1, it doesn't matter. So now, you see this here. The angle, omegas, for example, if you have two speakers, one of them is sending sound waves of, let's say, 1,000 hertz, and the other one is sending sound waves of 1,002 hertz. So omega 1 plus omega 2 divided by 2 will be about 1,000. But this one, omega 1 minus omega 2, or omega 2 minus omega 1, would be, let's say the first one is 1,000, the second one is 1,002. When you subtract them, you get 2 hertz, and you divide it by 2, you just get a 1. So this one is quick varying, and this one is slowly varying function. Okay? And I forget one thing. I forgot the time. There should be a t here, and there should be a t here. Yes, otherwise it's a constant function. Okay? So this varies quick. It has higher frequency, and this one varies slowly. I mean, just go to your graphing calculator, let's say, and for example, graph the sine of x, and graph the sine of 2x, and graph the sine of 3x. You will find that the sine of x looks like this, and the sine of 2x looks like this, and the sine of, so it's a faster varying function, the sine of 2x, and the sine of 3x will be 3 times as, you will pack 3 more in there. And you can imagine if this is just 1, it would be like the sine of the other one. If it's 1,000, it will vary 1,000 times within there. And so this is quickly varying, and this one is slowly varying. We will call this the modulation frequency, omega modulation. And it is just omega 2 minus omega 1. It's just the absolute value of them. All right? I'm sorry, divided by 2, the absolute value. And this one is just the average frequency, omega average. It's just omega 1 plus omega 2 over 2. And so people can write also this briefly as 2a times the cosine of omega mod times the time, and the sine of omega average times the time, modulation. Okay, so how do we graph this? It will look something like this. That's the outside. This is this one. And this one here will look like this. I'm sorry. Will look like. It's just a lot more variation. In the book, they have a better picture than the one I can draw. And you see within one cycle here and here, you will hear the loud sound once. Not just you will hear it once and then you're ready to start this next cycle. You will hear it once, and then the magnitude here, the amplitude here or here. So you'll hear it twice the loudest sound per cycle. So the frequency with which you hear the sound will be twice, so twice this. And that's called the beat frequency. So F beat will equal to twice omega mod. And so it is equal to twice omega 2 minus omega 1. And remember the frequency, divided by 2 pi, because the frequency is, because omega is 2 pi times f, so f will be omega divided by 2 pi. So just the beat frequency will be the frequency 2 minus frequency 1. Okay, frequency 1. So for example, here's an example. Let's say I have source 1 has frequency f1 equal to 452 hertz. And let's say you hear the beat frequency, if the beat frequency is equal to 2 hertz, all right, the beat frequency is to 2 hertz. Then the question is, f2 is what? What should f2 be? Well, I know that the beat frequency is f2 minus f1 in absolute values. So the difference between them is 2 hertz. So f2 could be 454 because 454 minus 452 is 2. Or it's 450 because 450 minus 452 is negative 2, but there is absolute values, that's also 2. So f2 ends up being either 450 or 454. Both of them can give you a beat frequency of 2 hertz. So that's an example there. Okay. And I think you notice there is a lot of trigonometry in this chapter, but I don't think it's a difficult chapter. You just have to pay attention to what's going on. Is it interference in time or interference in space? Interference in space is what we did for most of the chapter. Interference in time is the beats here. So interference in space, you have 2 sources and you walk around. You walk around and you hear loud sounds at some spots and maybe quieter sound at other spots. And when I say sound, it could be, if it's light, it will be bright spots and dark spots. Constructive will be the bright spots, destructive will be the dark spots. And if it's a string, it will be nodes and antinodes. The antinodes will be the constructive interference and the nodes will be the destructive interference. You walk around and you find those. So you have to change your position in space to see the interference, to see constructive and destructive interference. For beats, you just stand at the same position, and since the two sources, they have different frequencies, you will hear loud and quiet sound every now and then, with a beat frequency equal to the absolute value, the absolute difference between the two frequencies. I will now erase the board and do a couple of questions, few questions from the end of the chapter, from the end of this chapter. So let me erase first. So we get, so let's do here, problem number, let's do number 5. Number 5. From chapter, this is 17, chapter 17. Get my other pen. So it says, you have a standing wave oscillating at 100 hertz. So here's a standing wave oscillating at 100 hertz. So here it is. So you have 1, 2, 1, 2, like so. Let's see here. I think I have 3 5 peaks. 1, 2, 3, 4, 5 peaks. Yeah. So here it is, and it could like this. So that's similar to what we did in the lab. String vibrating. They tell us that this portion that vibrates is L equal to 50 centimeters or 0.5 meters, and the frequency we're told is 100 hertz. And the question is, what's the wave speed? Well, so what's the wavelength? The wavelength is you have 1 wave, 2 waves, 3 waves, 4 waves, 4.5. I think I have, oh wow, I have way more than, I have, it needs to be 1, 2, 3, 4, 5. Yeah, I should have stopped here. I have way more than they drew in the problem. Yeah, sorry. So this is L equals to 50 centimeters or 0.5 meters. The frequency is 100 hertz. What's the wavelength? Well, it looks like this is what? I have a node. How many antinodes do I have? 1, 2, 3, 4, 5. So this is F5 actually. And remember, lambda 5 will equal to 2L divided by 5. And so you get 2 times 0.5. And this is F5 actually. So 2 divided by 5. And so I get 0.2 meters. That's the wavelength. And therefore the speed will be lambda times F. But lambda times F, it has to be the same, lambda 5 times F5. So you have 0.2 times 100. And that gives me 20 meters per second. Okay, so that's that. Let's look at the next problem. So they say here, this is number 11. Number 11, you have a string here, and there is a mass hang on it, mass M. And we don't know what the mass is, but it is shaking like this. It goes back and forth, shaking as one piece in the fundamental frequency. And L is 90 centimeters or 0.9 meters. The wire itself, let me call this one capital M. The wire itself has mass little m equals to 5 grams. 5 grams. So 5 times 10 to the minus 3 kilograms. So let me just read the wording. It says a heavy piece of hanging sculpture, so this is a sculpture here, is suspended by a 90 centimeter long 5 gram steel wire. When the wind blows hard, the wire hums and its fundamental frequency is 80 hertz. What is the mass of the sculpture? So they're saying that the fundamental frequency, F1, is 80 hertz, okay? 80 hertz. So since the this is F1, let me find lambda 1. Lambda 1 would just be twice this. Remember, if the length is this, then lambda 1 will be twice L, and it is equal to 1.8 meters. And therefore, we can find the speed. Speed would be F1 lambda 1, or lambda 1 F1. And let's get my calculator. I get F1 lambda 1, so 1.8 times 80, that gives me about 144 meters per second. Okay. Now, since I'm given the mass of the wire and the length of the wire, why not calculate mu? We might need it. Mu would be the mass of the wire, not the sculpture. We're talking about the wire. So 5 times 10 to the minus 3 divided by 0.9, and so you get that, you get 5 over 0.9. That gives me 8.8888889 times 10 to the minus 3 kilograms per meter. And I know here there is tension upward and capital mg downward, and so the tension will be capital M times g. And I know that the speed of waves will be the square root of the tension divided by mu, and so v squared will be tension over mu, and therefore the tension will be mu times v squared. So, but the tension is capital M times g, and that's equal to mu times v squared. And so capital M would be mu times v squared divided by g. And so we get mu is this number here, 8.889 times 10 to the minus 3. V squared is, v is 144, but you have to square it. V is 144 and you have to square it, yep. And then you divide by g, which is 9.8. And that gives you the mass of this sculpture. So times 10 to the, let's see here, minus 3, and then times 144 to the power 2. I think I did something wrong. 8.889 over 1,000, okay? And then times 144 to the power 2. Yeah, that's better, divided by 9.8. So the mass of this sculpture is about 18.8 kilograms. Okay? And hopefully my answer matches. Okay. Oh, apparently I made a mistake here. 5 over 0.9 is not 8.88. It's, what am I doing? It is 5.555. Yeah, so this is 5.555. So 5.56. So this one is here, 5.55, 5.556. And so the mass would be slightly less. About 12 kilograms, they said? Yeah, about 12 kilograms. Okay. But the essence, I mean, the setup of the problem. Okay. Okay, sounds good. Next is some interference problem, but I think I'm running out of time. Yeah, let me do that in the next video.